Okay, now let's talk about some linear algebra. Let me remind you some linear algebra basics. So in linear algebra, if we have, as a maximal set of commuting operators of, say, mutually commuting operators, which are Hermitian, then their eigenvalue, their eigenvectors, then their, let's call them simultaneous eigenvector. Meaning that vectors which are eigenvectors of both, of all the operators which are commuting, form a complete and orthonormal basis, right? Right? Did you learn this about this theorem in your linear algebra course, or at least came across the statement in your quantum mechanics course? I know that in my quantum mechanics course I emphasize this, although I don't never prove it because of shortness of time. That's why in finite dimensional linear algebra, Hermitian operators are so important, because they give us the basis of a vector space.
I didn't see it in linear algebra, but I learned it in my quantum computing course.
Yeah. Okay. So in this case, in the case of SU2, this maximal set is J squared and J3, right? You could have chosen J1 or J2, but J3 is conventional, right? So that means that our vectors will be simultaneous. Our vectors will be simultaneous eigenvectors of these two operators, right? Of these two linear operators. So let's write these vectors as lambda m, where lambda is the eigenvalue of the J squared operator. And I'm going to use this notation from quantum mechanics, but this just means it's a vector. I could have used this, but let's just use the Dirac notation. No, this is just what it means. This is just a vector. Okay. And J3 acting on lambda m is m times lambda m. Okay. So here, both lambda and m are real numbers. All we know is that lambda is positive, but we don't know anything about m. We don't know if they're integer or half integer or anything like that yet. All of this will be revealed in time. The structure of the Lie algebra is very powerful, that it contains all this information, and we shall derive all that information. Okay, so this is a very, very important statement. Does everyone follow what I'm trying to say? So the idea is something like this. If you have some operator A and some operator B, or matrices, and suppose they commute, Now suppose that when B is acting on psi of B, some vector, you get an eigenvalue, you know, a B, right? And then now because they commute, if you now act A on this vector B of psi of B, what do you get? You get B times A of psi of B, right? But this is the same thing as B times A of psi of B, right? So that means that A times psi of B, hang on, yeah. So that means that A times psi of B is proportional to psi of B, right? Because this is just an eigenvalue equation, you know, which is the same as here. There is an assumption that the eigenvalue is not degenerate. If it's degenerate, that it requires a little bit more work, but you know, we won't go there. So this, what does this mean? This means that A of psi of B, if you write it equal, then there is some proportionality constant psi of B. So we see that if A and B commute, and B and psi of B is an eigenvector of the operator B with the eigenvalue B, then it's also an eigenvector of operator A with some other eigenvalue, possibly some other eigenvalue A. So we should label them both with both. Okay. So this is a quick and dirty proof that if you have two operators which commute, then they're you can have simultaneous eigenvalues, eigenvectors. Okay. All right. So